Ready to rock? Cool, good to go. Hello everyone, we are WAAM powder feeding mechanism. My name is Justin, David, Addison, Quinn, Charlie, Jason, and our advisor is Professor Norian. So what is WAAM? WAAM stands for Wire Arc Additive Manufacturing, and what it does is it uses an electric arc to melt a wire feedstock to produce large metal parts quickly. An example of one is shown in the image right there. Some of the limitations of WAAM: you can't easily make multi-material or composite parts. You have to deal with resistance stresses and rough surfaces with post-processing, and you have limited composite material options as well. So for our project, we have the opportunity to address limitations 1 and 3 by adding a powder feeder to WAAM, which would combine high-speed production with flexible material control, enabling us to make advanced metal matrix composites and multi-material parts.
So you heard metal matrix composites mentioned, but like what actually is that? So it's basically a block of metal with ceramic particles or fibers kind of dispersed throughout. You can see in this picture a couple different examples of types of MMCs. The one that we're mainly concerned about is the particle reinforced MMCs on the left. The benefits of doing this is you get a really good strength to weight ratio. You get a great thermal stability and better wear resistance than the base metal. And it can be used in a lot of applications, and especially in industries such as aerospace and automotive, anywhere the strength to weight ratio is really a big concern.
So now that you guys know about MMCs, you might be wondering, how are they made currently? So there are currently 2 main categories of MMC manufacturing. The first is liquid state. This is methods like stir casting and infiltration. If you look to the picture on the top there, you can see liquid metal being poured into a mold. Essentially, these ceramic powders are mixed into the molten metal and then poured into a mold and cast into shapes. And so the pros of this liquid state manufacturing is that it's suitable for low melting metals, and it's good for mass manufacturing simple parts. But the cons is that the lead times are super long, and it's really bad for complex geometries. And anytime you redesign something, you need a new mold, which could take more time. Next is solid state manufacturing, where the methods are like diffusion bonding or powder metallurgy. As you can see in the diagram on the right, it's essentially mixing the metal powders and the ceramic powders, and then using heat and pressure to bond everything, and then sintering it to make a nice strong bond. And the pros is that the bonding is super good, but it's long processing times, it's tooling intensive, and requires extensive pre and post processing.
So then you know how MMCs have been produced traditionally, but it has actually been used with wire arc additive manufacturing already. And this has been done with 3 main methods, which is cord wires, coated wires, and composite wire feedstock. For cord wires, you can see a picture of it here. It's just like a little tube of metal, and you shove a bunch of ceramic powders in the middle of that tube, and then you use that to feed through the wire arc like robot arm. The coated wires is where you take kind of just a regular feedstock and you spray ceramic powders on the outside. And then the composite wire feedstock is where you draw a like already made MMC into this like feedstock. And so they have a couple limitations, which are you're kind of limited to the length of wire that you have. They can be really expensive and difficult, especially with the composite wire feedstock. The ceramic makes that material more brittle, so as you draw that into a wire, it can break really easily. And mostly, there's no flexibility to adjust like the material properties. You're locked into like this specific amount of ceramic in your feedstock.
So moving away from MMCs, we're back for powder feeding. Most off-the-shelf powder feeders have 3 main components, which are metering, transportation, and deployment. Current powder metering techniques are screw, rotary, pneumatic, and vibration. Picture on the right is an image of a power screw metering system, where the screw turns and the powder is pushed down. And then the second image is a pneumatic powder feeder metering system, where air pressure moves the powder. And then in terms of transportation solutions, can vibration, pneumatic, and gravity. And then the advantage of having powder feeder with WAAM is that it enables continuous reinforcement at a low cost using off-the-shelf powder, which reduces the cost and increases scalability for MMC manufacturing.
So who cares? So there's a growing market demand for metal additive manufacturing, which is projected to grow up to $5.4 billion by 2027. WAAM is also considered as a promising technology for producing medium to large scale metallic components and structures. So that includes like things like a flisk, propellers, a ship propeller down there, and also relativity space using the WAAM systems to design rocket bodies. And so those industries include like the aerospace, automotive, shipbuilding, agriculture, mining, oil, gas, and defense. All of these require a lot of strong heat and wear resistant metal composite parts, but they're very limited by cost and manufacturing challenges. So additionally, there's also the material science R&D field where the combination of a powder feeder combining it with MNC production and 3D printing capabilities would allow them to experiment with new alloys, composites, grade materials for higher hardnesses and wear resistance.
Our solution. So in order to address the shortcomings of some of the current MMC manufacturing methods, we're going to be designing a powder feeder that be mounted onto a robotic arm of an existing wire additive manufacturing machine that's on the Burlington campus. And this is going to enable us to create large metal matrix composite parts, which are continually fed by powder. This is a flowchart of what a wire arc additive manufacturing assembly looks like with powder feeding integrated. So we'll be focusing on the powder feeding or powder metering device, which will need to be integrated with the controls of the robot, and then also the powder delivery mechanism at the level. And then what's next? We've done a lot of good research into why this is important and the opportunity. And then what's next is going to be selecting a method for some of the critical design aspects, including the metering, feeding and delivery, which Addison mentioned. And so we're going to look at some of the different parameters that we need to take into consideration like powder flow rate, accuracy, and reliability. And then we're also going to be visiting the Burlington campus so we can actually get eyes onto the assembly and look at the footprint and identify how we're going to be mounting our solution to it. Thank you. I think it's my turn.
Yeah, sure. No, please. No, I honestly, I'm sorry, folks. I can't think of, off the top of my head, I can't think of a single way to make your presentation better. Go ahead. Oh, yeah, not too bad for that. No, you're allowed to say yours. I can't think.
All right, now we're gonna hate Sean. I'm just kidding. Okay. I thought, no, actually, I do echo what Professor Goldstone said about your understanding of the project is very solid. Also, your breaking down of the technicalities of it was very cool. So it looks to me like I see 6 people who are really into this project and figuring out all the ins and outs of it. I think maybe once or twice the figures were a little small, so it's hard to make out, not the fonts, but just the size of the figure, but you did interact with them well. And you were just right on time, which I would say is okay. Just keep an eye on that clock, right? So try not to let it get to that point, but otherwise, you somehow managed to squeeze all this technical content in and help walk us through it in 7 minutes. That's good. Yeah, so I think it was a good presentation. Yeah, thank you.